Hi everyone, and welcome to today's Chemistry Daily Booster. This is number 8 in our Paper 2 series, and this is going to be one of the advanced information listed topics for both foundation chemistry and higher tier chemistry. What we're going to look at are some of the key bits from section 5.1 of the specification. So to start off with, we're going to look at the calculation for percentage yield. Do remember, in chemistry there is no formula sheet that they give you, so any of these calculations you need to learn the formula because there's not a guarantee they're going to give it to you in the question. If they're being nice they might, but they also may not. To work out percentage yield then, it is the actual yield divided by the theoretical yield, and because it's percentage we times that by 100. So what we're going to do then is actual yield is always going to be given to you in the question. They will tell you that in the experiment they made 5 grams or whatever it is. So that's your actual yield. Theoretical yield is what we need to work out. So what we're going to do here then is, in order to actually do this calculation, there are 4 steps to success, if you like. Step 1. Calculate the relative formula masses. You've got a periodic table, so all you need to do, look at the formula, look at that particular element on the periodic table, and then add up the relative atomic masses to get the relative formula mass. Step 2. Calculate the sum of the relative formula masses using the balanced equation. By that, what we mean is your relative formula mass for that particular substance times however many moles there are in the balanced symbol equation. Step 3, calculate your theoretical yield. So the way we do this, mass of the limiting reactant divided by the sum of your relative formula mass for the reactant multiplied by the sum of the relative formula mass for the products. Finally, because we've got a theoretical yield, all you do is actual divided by theoretical times by 100, and you've got your answer there. Depending on the style of question, they could just literally tell you the actual yield and the theoretical yield in the question, and then just ask you to calculate percentage. That's the nice way. The slightly less friendly way is expecting you to calculate theoretical yield as we've just outlined here. So just make sure that obviously, if you're doing higher tier particularly, that you know how to do this. Foundation, I'd be sort of hedging my bets a little bit more on the fact they just tell you. Can't guarantee they do that, but that would be my gut feeling. So let's have a little look at an example question here then, shall we? Nitrogen reacts with hydrogen to make ammonia. So we've got N2, 3H2. Let's add our reversible reaction sign in that's missing there to make ammonia. Calculate the theoretical yield of ammonia when 12 grams of hydrogen reacts with an excess of nitrogen. So we are told we have 12 grams of hydrogen, nitrogen is in excess, and we need to calculate the theoretical yield. First thing we're going to do then is, because nitrogen is in excess, then we don't care about nitrogen at all. Ignore its existence. It's irrelevant because it's an excess. That leaves us with hydrogen and ammonia. First thing, we need to calculate the relative formula masses. Periodic table at the ready, find hydrogen at the top left. Hydrogen has an atomic mass of 1. There are 2 of them, so 2 times 1 is 2. Do the same for ammonia, NH3. So nitrogen, atomic mass is 14. Hydrogen we already said is 1. There's 3 of them, so 14 plus 3 times 1 gives us 17. Next up, we need to work out the sum of the relative formula masses. So times what we just worked out here as our relative formula mass by the number of moles up here. So what we can see first of all is, for hydrogen we have 3 moles of it, so 3 times 2 is 6. Ammonia, 2 moles, so 2 times 17 gives us 34. We need to calculate the theoretical yield then, so the mass of our limiting reactant, that's going to be our 12, okay, because it's in the question there, mass of our limiting reactant, 12 grams of hydrogen, so 12 divided by the sum of the relative formula mass for our limiting reactant. So find hydrogen, Here's our sum, it's 6. So 12 divided by 6, and then we've got to multiply it by the sum of our relative formula masses of the products. So our product is 34 in this case. So 12 divided by 6 times 34 gives you 68 grams. Second part to that question, if the actual yield of ammonia made was 54 grams, calculate percentage yield. So percentage yield is actual divided by theoretical times 100. They've told us that the actual is 54, so 54 divided by 68, worked out in the earlier question, times by 100, 79.4%. This is one of those questions where, if they give you part 1, calculate the theoretical yield, part 2, calculate percentage yield, if you can't remember how to do part 1, don't leave it blank. Literally, stick whatever number you want in there. As long as you've written an answer and you use that answer in part 2, you will get what we call error carry forward marks for part 2. If you leave it blank, you get nothing. So you've got to write something in part 1 that you then use for the part 2 calculation. So even if you have no clue what the answer to part 1 is, pick a number, stick it in there, and use it for part 2 that hopefully you do remember. As far as percentage yield goes then, you should have an answer between 0 and 100%. If you don't, flip the bits the other way around. Chances are you've divided the wrong way. So if you've got an answer that is above 100%, just flip your division round and then you should get it right. But what we're going to find is, in virtually all cases, your percentage yield is going to be less than 100%. Simple reasons for this. Your reactants may react in a different way than expected when we're reacting them in air. The reaction may not go to completion, meaning some of the reactants are left over, or you can lose some of the product. In terms of the loss of product, look at the actual scenario they've given you to try to be a bit more specific. So if you're heating in an evaporating dish, for example, some bits might spit out. So just try to relate it to the scenario they give you there. But those are 3 key ways that we would lose some of our actual product and therefore not have 100% percentage yield. Calculation number 2, atom economy. When we're talking atom economy, this is a measure of how many atoms from the reactants end up in our desired product. So if you have a low atom economy, basically that tells us only a few atoms from our reactants end up in the desired product. If it's a high atom economy, lots of them end up in our desired product. We would like lots to be in the desired product, ideally, because the higher the atom economy, the more sustainable the process is, because we're going to be generating fewer waste products. How do we calculate atom economy? The sum of your relative formula mass of your desired product divided by the sum of the relative formula mass of all products, and it is going to be a percentage, so times by 100. So realistically, desired product divided by all products. Reactants are irrelevant in this. What we now come on to then is looking at how we select a reaction pathway when we've got more than one possibility at our disposal. So what we're going to look at then are certain factors. First one, yield. You want a high yield. So higher is better in terms of our yield there. Atom economy. Again, the higher the better. So you are going to be looking for one with a high atom economy. Rate of reaction, we want that to be as fast as possible. Byproducts, ideally, as few as possible. And the equilibrium position if we're talking a reversible reaction. So by that we mean what conditions would we need to make the equilibrium position suit our purposes. What they could do is give you a little table of information about a couple of different reaction pathways to get the same end product and ask you to justify your choice of which one we should use. So look for the higher yield, look for the higher atom economy, the faster rate of reaction, the one that's got a minimal number of byproducts, because that's going to mean it's the more beneficial pathway to select. Justify it using the information in the table. We do have a couple more calculations to go in this booster. We're going to have a look at concentration. Now, concentration could be expressed as grams per decimeter cubed or moles per decimeter cubed. First thing, if we're looking at one of these calculations, chances are they're going to give you a volume in centimeters cubed. We need it in decimeters cubed. So to convert your centimeters cubed to decimeters cubed, divide by 1000 first of all. Then, in order to actually get your concentration, what we're going to do is, depending on what they've told you in the question, it's your kind of amount. Whether that is in mass or in moles, then it doesn't really matter, because it's either the mass in grams or the amount in moles divided by the volume. So that then gives you your concentration each time. So amount of your substance divided by the volume in decimeters cubed gives you concentration. Final calculation of today is looking at our gas volumes. So what we're looking at here then is when we consider any substance, when it's in the gas state, 1 mole of that substance is going to occupy the same volume at the same temperature and pressure. And that's what we refer to as the molar volume. So at room temperature and pressure, that's going to have a very specific number of 24 decimeters cubed per mole. This is going to be our very useful little formula. The volume in decimeters cubed is the amount in moles times 24. Basically what that means is if they tell you in a question that you need to work out the volume occupied by 5 moles of any random gas you like, then all we've got to do is the amount in moles times 24, and that gives you the volume. If they were to give you the volume occupied by a random number of moles, then you would do that volume divided by 24, and that will give you your amount in moles. So realistically, remember 24, and then remember volume is amount in moles times 24. You can then use your triangle to rearrange as needed. If there are bits that we've gone through in today's booster that you'd like to go through in a bit more detail, then head on over to the C5 playlist on the channel where you can find these in a greater level of detail. You can also use obviously the information in your revision guides, your class workbooks, and I do suggest looking at some paper 2 chemistry papers from the past just to get a bit of a feel for those style of questions. Then of course don't forget to join us again tomorrow for our next daily booster.